In some cases, we care more about surface slopes than we do heights, or certainly care as much, and the measurement of the slope is important. It can be important to things like appearance or dullness or shininess, and a surface that has lots of fine features that are steeply sloped can look kind of fuzzy or gray to our eye, but a surface that's made up of round lumpy features may feel more or look more shiny to our eye. This reflecting of light is related to the slope of the surface. Now, we have parameters in surface texture related to surface slopes. If we see a parameter with a D in it, think of D as a delta. It's the delta or the slope at a given point. So this particular point on the surface right here has some slope, some delta, some amount of change in height relative to some amount of distance in length. If we look at a surface texture in terms of its slopes, we'll see that we have slopes that could perhaps be very steep in some places. They could be zero in other places. In some cases, the slopes are steep downward. In other cases, they're steep upward. So if we walk all the way along this surface and look at every point along the way, we're going to have lots of slopes. Let's represent these slopes this way as a distribution in this case. So we're going to have a lot of slopes that are basically close to zero, and then we're going to have some positive or upward slopes and some negative or downward slopes along the way. This surface has a lot of zero slopes. There are lots of surf points that are close to the peaks and close to the valleys. These slopes are very, very close to zero around the peaks and valleys. And then there are slopes on the sides that may get steeper and steeper. The distribution of slopes is useful in describing the surface texture. A surface that's kind of randomish in terms of slopes will have a standard deviation of slopes, and just like the RQ parameter, where the standard deviation became RQ, in this case we're looking at deltas or slopes of the surface. So we have R for roughness, delta, which we represent as D, and Q for standard deviation. The standard deviation of slopes is RDQ. Now, a surface that's rather lumpy and smooth could still be tall, but within the height is relatively smooth in terms of transitions, might have a relatively low RDQ. It's kind of low because we don't have crazy extreme slopes. But a surface that's perhaps even smoother, it doesn't have as much height, but has a lot of extreme slopes, could have an RDQ that's very high because we're measuring slope, not height. In fact, this surface right here with the sine wave, we could have it very low like this, and if we add some noise to the same sine wave, we now have high local slopes, and these two surfaces could have the same RA, the same roughness, but we would again have an RDQ here that is also high, because RDQ is all about measuring local slopes along the way, and these are extreme slopes. They're extremely vertical or extremely steep to have the high RDQ number. So think of RDQ as the range of steepness along the way. A surface that's not very steep along the way will have a low RDQ. A surface with lots of steep features will have a high RDQ. This will appear shiny, whereas this one down here will appear more dull.